So enthalpies of solution. Enthalpy of solution is a process that takes you from having a bunch of salt and dissolving it to see whether the whole thing is going to end up being exothermic, endothermic, and what are the steps that need to happen in order for you to actually dissolve a salt. First, we're going to have a container filled with water, and we're going to insert a bunch of salt. We'll use sodium chloride or whatever. The very first thing that needs to happen is your sodium and your chlorine need to split apart. You're actually breaking the bonds in between sodium and chloride. Second, we are going to get the individual water molecules, and they need to split apart. Why are they doing this? They are doing this to make space for the sodiums that they're about to surround. And then the third step is your water is going to surround the specific sodium and chlorines. Sodium is positive, so the oxygen side of the water, because oxygen has a partial negative attached to it, is going to surround the sodium. If you're ever asked to draw this in an FRQ, always include at least one of each ion and 2 water molecules around each ion. That's just a loose requirement of sorts. If you don't do that, chances are they won't give you full credits. And I've graded a number of exams where that is the case. So positive attached to chlorine, and then we need to put another water right here. 3 steps in this process. So again, sodium chloride splits up, water splits up to make space for sodium chloride, and then the water surrounds the sodium chloride ions. Step 1 is the lattice energy. That is the energy that it takes to break sodium chloride bonds. Step 2 and 3 are going to be known as hydration energy. Then they will refer to that term, hydration energy. This is steps 2 and 3 of the enthalpies of solution process. And they each have different values in terms of enthalpies. So let's take a look at that for a second. Step 1 requires you to break bonds. In that case, delta H has to be positive. It requires energy for that to happen. Here in step 2, we're taking water and we're pulling them apart. Again, it takes energy to do that. So this section is also going to be positive. And then in the third one, we are forming attractions with the water molecules surrounding the salts. This is going to release energy. Steps 2 and steps 3 will always sum to have a negative energy, enthalpy value. Hydration energy is always negative. Lattice energy is always positive. Whether or not the entire reaction ends up being exothermic or endothermic depends on these two. If the lattice energy is greater than hydration energy in the enthalpies of solution process, so the positive number is bigger than the negative number, you get an endothermic reaction. And when the lattice energy is smaller than hydration energy, you get an exothermic process. You shouldn't be memorizing this, and you should not be memorizing any of these bits of information. The only things you should be memorizing are what are the actual steps and what's the name for these things. So steps 2 and 3 are just hydration energy, and step 1 is lattice energy. As far as the signs, you have to be able to deduce what it's going to be. Here, we're breaking bonds. It has to be positive. Here, we're breaking IMFs. It has to be positive. Here, we're forming IMFs effectively between sodium and water. That has to be negative. Steps 2 and 3 always need to be negative. You pretty much do have to remember that. But then common sense tells you if it's positive, that would mean the enthalpy of solution for every single salt is going to be endothermic, but that doesn't really make any sense. So this has to be negative, and step 1 will be positive. Then, in reference to magnitude of both of them, that's what's going to tell you whether the entire salt dissolving process is going to be endothermic or exothermic. Moving on, we have calorimetry. The common way you guys see it is with a coffee cup. And there are two embedded coffee cups actually. Oh, that one came out bad. In the first coffee cup, we're going to have a bunch of solution, a thermometer, and some reaction. In the second coffee cup, we're just going to have air. This air acts as an insulator to make sure that most of my reaction stays inside and we're not losing too much heat into my external surroundings. Here, you're going to put salt, and it's either going to be exothermic or endothermic. It's going to release some energy or absorb some energy. To find out how much energy got released or absorbed, we have Q equals mc delta T. We can look at Q for the solute, and I'll call that Q1, M1, C1, and delta T. And then the same thing for the water. Let's assume an exothermic process, just so we don't have to use random terms. If we're taking a salt and we're dissolving one that is exothermic, the energy released by the solute is the one that's absorbed by the water. So I can make that same exact equation for the water. They might not give you the mass of water, you might get instead the volume and the density, but you also know that density is going to be equal to mass divided by volume. So given these two things, you can find out the third one. And then C1, specific heat values for both the solute and the water, change in temperature, and that's going to be, depending on what the question, how the question is worded, may be the same, may not be the same. If you were to put, say, a very hot piece of metal into water, then obviously they're not going to be the same. The hot piece of metal, so our solute, quote unquote, in this case, is going to have a very big change in temperature, while the water, chances are, to be a lot smaller. But the main thing is that because the energy released by the solute is the same thing as the energy absorbed by the water, again, assuming exothermic, these two values are going to be the same. So what ends up happening, M1 C1 delta T is going to equal M2 C2 delta T2. And again, these values may or may not be different. Chances are they're going to be different. You have to read the question carefully. And then comes another problem that I've noticed. So when we're talking about the water, some questions are worded in a way that here you would use only the mass of the water, while others are worded in a way where it's the mass of the water plus the solute. So M2 is either going to be mass of the water or mass of the water plus solute. In the case that it's mass of water plus solute, the specific heat capacity would technically change too. So it gets to be a little bit of a gray area that, to be honest, for even some FRQs that have been published by the AP a little bit further back, it just didn't make any sense the way they were wording it. So you have to be very careful. My best advice would just be practice a ton of these calorimetry related questions. Take your time and read very, very, very carefully what's being asked of you. If you have any of the more common AP review books, so Princeton, Barron's, all that kind of stuff, they make mistakes very often. So you really need to be careful. Take this to your teacher, have a discussion with them about whether they think it should be the mass of the water or mass of water solute and all that kind of stuff. Debate amongst your classmates, whatever. Get as much practice in as you can, specifically with regards to this. Now, moving on, we're going to have changes in entropy. What is entropy? Entropy, to put simply, is going to be a measure of disorder or randomness in a given system. If I increase my entropy, so I have an increase in my change in entropy, that means there is more disorder. If I have a decrease in entropy, there is less disorder. How do we actually view this? For starters, the simplest way is going to be quantitatively. They're going to just give you numbers and you'll have the same equation from before. Sum of all the entropy values from the products minus sum of all the entropy values in the reactants. You have this equation too, so you definitely don't have to memorize it. Just products minus reactants. Same exact process we did with entropies of formation. Now, the more interesting ways are going to be from the equations. Say you have A which is a solid, plus B, which is another solid, forming to make C, a third solid. Will this have an increase in entropy or a decrease in entropy? Here, every state of matter is solid, so we don't have to worry about their states. But we have 2 moles on the left-hand side and 1 mole on the right-hand side. I have decreased my number of moles, so this will have a negative value for my change in entropy. There is less disorder because there are less things, there are less molecules. The third way is with the states of matter. So a solid has less entropy than a liquid, which has less entropy than a gas. If you take A from a solid to the gaseous state, this will have a large increase in entropy. And that's the qualitative version of looking at these things. You're going to be asked often, certainly, to look at it just from this standpoint and say, you have a spontaneous reaction. What do you expect to happen with entropy? Or does it make sense what happened with entropy? And justify based off of what's given. And again here, something going from the solid state to the aqueous state also would feature an increase in entropy, but that'd be a little bit different. We can't compare that to liquids and gases. It would just be more entropy than that of a solid. Aqueous is only going to go back and forth between solid and aqueous. Also, last topic to talk about is Gibbs free energy. So what is Gibbs free energy? Gibbs free energy is a measure of spontaneity. You can use thermodynamically favorable as well. Thermodynamically, I spelled that wrong. No, favorable. The term that's used more commonly is spontaneity nowadays, but if they use the other term, it means the exact same thing. A negative value is spontaneous. A positive value is not spontaneous. So, in reference to what we're going to be talking about the next couple minutes, it's not that any of these is preferred, but just to give us a reference point when we're actually talking about these questions, we're going to say that reactions want to be spontaneous. Now, again, that's not necessarily the case. It's just that when they are spontaneous, they happen on their own. They don't want to be spontaneous, but we're going to view it that way just to give us a frame of reference for things that are quote unquote needed or favorable, really. More spontaneous is in reality what I'm trying to say. How do you do this? First, we can do, again, products minus reactants, but you will hardly see this. Reason being, there's tons of other ways to be asked this. Your main formula, that being said, your main formula for Gibbs is delta G is equal to delta H minus T delta S. And here is where things start to get a bit more interesting. For starters, let's look at units. Delta H tends to be given to you in kilojoules per mole of reaction, whereas delta S tends to be given to you in joules per moles of reaction Kelvin. There is a clear mismatch in the magnitude of the two. You can go back and forth and technically give an answer for enthalpy in joules and give an answer for entropy in kilojoules if you wanted to, unless they ask specifically. It just so happens that more often than not, delta H is in kilojoules and delta S is in joules. That being said, you are going to have to make a change in magnitude for one of the two. It doesn't really matter which one, just depends on what they're asking for Gibbs, what magnitude. Doesn't matter, as long as you include the right units. So be wary of that. Now, if this whole thing ends up being negative, then that means you have a spontaneous reaction. If the whole thing is positive, you do not have a spontaneous reaction. But what about this temperature term? How does that affect things? We have to analyze the temperature dependencies for Gibbs free energies. Given high temperatures, certain things are going to happen. Given low temperatures, other things will happen. Let's rewrite our formula for Gibbs. It's delta H minus T delta S. Here we have the same thing. So based off of this on its own, what do we expect to be spontaneous and what do we not expect to be spontaneous? For starters, if we have a delta H value that is negative, so an exothermic reaction, this is going to be spontaneous. Why? Delta H is negative, a negative number goes in here, the whole thing, well, that will contribute to making Gibbs negative. If we have a value in entropy that is positive, so more disorder, that is again going to be something favorable. It will cause a spontaneous reaction. When both of these things occur, your reaction is always going to be spontaneous. What we have to see is what happens with regards to temperature. Delta S is positive, positive times the negative stays negative, so that whole thing would end up being negative, given that delta H is exothermic. But what does temperature do? Let's look at this under high temperatures. No, let's look at it under low temperatures first, actually. Under low temperatures, the condition would be that T is going to approach 0. When T approaches 0, anything that's being multiplied by T would also approach 0. So this entire term will be sent to 0. Then we are left with Gibbs is just going to be approximately equal to your change in enthalpy. At low temperatures, spontaneity is driven by changes in enthalpy. Why is that the case? Well, that's exactly what we just proved. Temperature approaches 0, this whole thing gets ignored. So a low temperature reaction that is endothermic will never be spontaneous because this whole thing would be positive. But a low temperature reaction that is exothermic will always be spontaneous because this whole thing will come out to be negative and Gibbs would be negative. What about the case with high temperatures? In a case of high temperature, and they always say extremely high temperature, T would approach infinity. If T approaches infinity, and infinity is it's an incredibly big number, it's infinitely big, that's the whole point. How much does delta H matter? In that case, effectively delta H is irrelevant as far as the Gibbs calculations are concerned. So now this section goes to 0. And we're left with my changes in Gibbs are going to be approximately equal to negative T delta S. Under high temperatures, you are then driven by changes in entropy. If I have a high temperature reaction with low disorder, that is never going to be favorable, or a decrease in disorder. Reason being, a decrease in disorder would mean this is negative, negative tends to negative is positive, whole thing ends up being positive. That's not spontaneous. Versus a high temperature reaction that has an increase in entropy will always be spontaneous because Gibbs effectively reduces to this, positive times the negative is a negative, and then all of Gibbs ends up being negative. When you have an exothermic reaction with an increase in disorder, that is always spontaneous. Always spontaneous. And when we have an endothermic reaction with a decrease in entropy, that is never spontaneous. Every other case is going to depend on whether we are looking at a low temperature or whether we are looking at a high temperature. And that wraps up this section. Let me know what you think down in the comment section below. If you found this useful, give it a thumbs up. Thank you very much, and take care, everyone. See you next time.